So this is a presentation I prepared a few weeks ago, trying to summarize kind of the state of building large language model in 2024, where we are, where we stand, what we know in the open. And a lot of things actually in this presentation have been done by Chinese team and also by a team at Tsinghua. So congratulations. And many things here will not be new for some of you, but maybe it's still interesting to see them gathered in one place. Just a couple of words about me. So I'm the Chief Science Officer and co-founder of Hugging Face. I created the transformers and the dataset library in Hugging Face. And recently I've been moving a bit from open source to do more like open science. So trying to share recipes and knowledge around AI, basically. And one of the reasons is I found AI research to be a bit more close now than it used to be in the past. And I think it's too bad. I also wrote a book called Natural Language Processing with Transformer, but I'm obviously a bit biased because I wrote it. But yeah, it's quite nice. Today, so I go basically over quickly what is Hugging Face, and then I dive in what make a large language model in 2024. So what is Hugging Face? Well, Hugging Face is built around something called open source. So here I present a bit the difference between open source and closed model. It's also a little bit biased because I like open source more than closed source. But there is a lot of things that are quite interesting when you work with an open model. And quickly, I summarize them here. In terms of security, you can just host the model on your data center or on your laptop. So I think it's very nice that you keep all your model on your laptop, for instance. You can control much more open source model because it's like an open box, just like open source code, right? You can customize it if you want. You can train it more. You can fine tune it. You can change a part of it. It's very transparent. So this is, I mean, there is a gradient in transparency. Sometimes they are just very, very open to the point that you know which data was used, which code was used to make it. And sometimes you only have the weights that are open, which is less transparent. But in general, it's much more transparent. At least you know what is the model and what part maybe is the surrounding systems that kind of help the model to work. In terms of cost, it can be quite cheaper. And in particular, you often find smaller models in open source, which can be very cheap if you just run them on your own laptop, for instance. The latency can be very low, in particular if you run it locally or if it's a smaller model. And the quality of open source, I would say, is the limiting factor at the moment. It's typically the performance are less high than the closed source model. But also open source models have been catching up quite strongly in the past month, in the past year. A couple of very impressive Chinese models like Yi or like DeepSeek or like the mini CPM. So all of these models are catching very strongly with closed source model. So it's very exciting, I would say, in 2024 to work with open source models. So Hugging Face is a hub to host model, datasets, and demo. We have a lot of models. Actually, this is already slightly outdated because we are now close to 1 million models. It's growing exponentially. We have over 100,000 datasets and roughly between 2 and 4 million users on Hugging Face. It's used pretty much everywhere, or at least in many organizations. And we see this sometimes as kind of an independent, like third party, between all the very large organizations that exist in the AI field. So we provide many libraries that are all also open source and that can be integrated at various places in the model development or deployment. Here, for instance, Transformer Accelerate are libraries that, and diffuser or like data sets are libraries that you can use to build models or to use them or to do research on them. And then you can deploy with more like inference API or spaces. We have this a big open source ecosystem. We started with these 2 libraries. And then we built quite a lot of others. So Radio is very nice to do quick demo to showcase a model. SafeTensor is a way to store safely your model, because Pickle is quite dangerous actually. Transformer.js is a version for JavaScript, and we have many other libraries that are, most of them are quite widely used. So this is for Hugging Face, and let me now talk about large language model a bit more. So the workflow to make a large language model is to prepare the data. So for each of these, we do have also an open source library that you can check, where you have like the recipes for everything I discussed today. So for data preparation, we have one library called Data Trove. And then you want to train your model efficiently. So we have a library called Nanotron for that. You want to evaluate it to understand how good it's performing. So we have something called LightEval. And then often you want to fine tune and align the model so you can use it as a chatbot, for instance. So this is usually done using a technique called RLHF. And we also have a nice library called TRL to do this. And then once your model is trained and fine tuned, you want to deploy it. And so generally you will like to quantize the model so that it can be smaller and run faster. So you can use bits and bytes. And then you will need to deploy it in production, for instance. And then we do have one nice library called Text Generation Inference. That's quite useful for production use case. Just a note on the carbon footprint and LLM. This is a bit unfortunate because today I would say there is some interest to limit a bit the energy we use to make it more rational for climate change reasons, because we're running out of some sorts of energy supply, and LLM do require quite a lot of energy to be made and to be used. And so there is a question whether, if you're doing something, do you really need an LLM for this? And this is kind of a flow chart to know. I would say if you have a specific task in mind, you should really ask yourself, do I need to pre-train an LLM first? Most of the time, you can start with a pre-trained LLM already created by someone else. And that's why we have so many open source models on the Hugging Face platform, right? And you can just fine-tune this LLM. So very likely, I would say the discussion I have today, which explains how to build this LLM from scratch, is a little bit over what you need to do. And then when you fine-tune only, you will want to select a compute-efficient model if possible. So typically, you can try to find the smallest LLM that works for you. For instance, right now, there is a lot of good quality 7B model and even 3B model. So you could start with this, you could quantize it, and you could also deploy it in a setup where you have a good energy mix. Now, if you need to pre-train a LLM, for instance, say you only have English-only models, right? Or like the only good models that are out there are English-only, so you need to pre-train one. Then it's nice to think a little bit about the whole circle of life of the LLM. So in particular, if you think you will deploy it in production, like at a large scale, you might want to train a smaller model for longer than maybe some optimally sized model for the lowest loss. So usually right now, people tend to train quite smaller model than they were training a couple of months ago. And they train it for much longer so that you reach the same performance. But when you deploy it in inference, it's a lot cheaper. So yeah, a couple of notes. But now let's dive in how to prepare data. So one thing important here is we tend to forget about the data because it's a little bit less exciting than the model, right? We all like to think about how to arrange these layers, how to add the layer norms, all the trick of deep learning. But the reality is everything, or like, this is not by me, and this citation I put, the top one is by Amanda, who work at Anthropic, and the bottom one is from someone at OpenAI. So they are basically people who kind of know what they are talking about, I would say. And both of them kind of say that all behavior just come from the data. So if your model is not doing what you want, it's just that you didn't put the right data in. There is no real magic in this model, even though we would like to think they are a bit magic. But the reality is, no, they are not magic. So thinking a lot about the data is usually just the right way to think about deep learning and large language model. This was a nice video. I don't know if you get the sound, but basically there's a lot of discussion every year with rich people thinking how to save the planet. And this guy was saying, well, we just need to think about taxes and other things we never talk about. And I think it's a bit the same in LLM. There is one topic we almost never talk about, which is data. And that's actually the only topic we should almost be talking about. So it's surprising how big the difference is between what we talk about and what is really important. So now let's dive into important things. Actually, this is another nice citation from Yi, the nice open foundation model by Zero1.ai. And they also say that underlying assumption is when trained on extensive data of high enough quality, a standard architecture can exhibit advanced capabilities. So now, how do you prepare your data? So here is a set of papers, recent paper, if you want to read. They're all quite good. I could add one very, very recent from Hugging Face, actually, which is the FineWeb paper. It's a development of RefineWeb. So you can Google it. I can add it. We published it just a couple of weeks ago. And it's also a nice report on how to build this data. You will have several stages in LLM training. You will have a pre-training stage, instruction tuning stage, or alignment, and even more specific in-context learning or different fine-tuning stage if you want. And for each of these stages, you will actually want a different type of data. So I'll focus on the pre-training stage, and here what you want is to train a very general purpose model. You want maximal coverage. You want to train on massive quantity of text. So nowadays, people train on at least 1 trillion of token. And I would say it's kind of the minimal. It's much more like reaching 10 trillions of token now. And the challenge here, there are many challenges. One is you want to maximize the diversity and the coverage. As I said, your model will not invent any new behavior. So you have to basically have everything in your pre-training data set. You want to maximize the quality of the data. And you want to try to measure a bit the quality. And that's really hard when you billions or trillions of token, because it's so big. It's hard to know. So here is one typical pre-training cleaning pipeline. It's from Yi, and that's quite standard. That's what we do as well. You will collect your data, filter the language. You will have a set of filtering steps to remove like lower quality data, a set of deduplication steps, and even some topic filtering if you want to emphasize some specific part of your data set. Here is another example. This one is from RefineWeb, and that's roughly the same stage. You start from the internet, command crawl. You will only keep the language you need. So if you keep only English, you remove roughly half of the command crawl data set. And then you will have a set of filtering, basically, followed by duplication. This is yet another example. So where do we start from? To start from, you want some very, very large data source. So basically, you want to find a copy of the whole internet. So for English, usually we use command crawl, which was crawled by a non-profit in the US. For other language, you may want to use other crawl or even to crawl yourself the web. For code, which is also quite important, you also have several very large repository. One is GitHub, and another one we work with is a Software Heritage, which is a bit like command crawl. It's a non-profit who has been crawling and archiving code on the web. You can add some curated data like Wikipedia, or if you find some books on books, there is a bit the question of copyright because some books are copyrighted, obviously. Wikipedia, you can add it, but also it's just on the internet. So basically it's also in common crawl. So if you add it manually, you just upsample it somehow. And very interesting recent trend is to add synthetic data. So what is synthetic data? It's data that's generated by LLM. Just to show you a couple of examples here in order of what we did at Hugging Face, we did a synthetic data set called Cosmopedia. And we are actually going to release probably next week a second version of Cosmopedia. The nice thing about synthetic data is you can control quite well what is in the data. So you can make, you make some prompts, and then you generate. I mean, there is a very nice data set that you probably know well, like UltraChat, who are fully synthetically generated. Given the performance of LLM today, the quality is actually quite high. Here you see a little bit what's in the data sets, but I'll let you read. For code data, if you want to start from something that has been pre-processed, we also released a very large data set called the Stack. The version 2 is really huge. It has almost 1 trillion tokens, and it's in many programming language. It's derived from the Software Heritage Archive. From what data? You should check the FineWeb blog post, and we'll post it at the end. So now let's cover a bit the pipeline steps. The first one is language filtering, because you don't really want to spend energy working on language that you don't need at the end, right? So fast text is quite a nice one, and that's the one we use usually. And then you want some quality filtering, and there is two big type of quality filtering. One is to do some statistics on what is in your data, like you count the repetition of characters, you count the ratio of character in the document versus line break, for instance, the mean length of the line. You can remove some outliers from your data sets. And the nice thing is when you do this type of heuristic statistics, you really know well what you are removing. Yeah, I remove it because it has more line breaks than the normal ratio. So you have quite a good transparency and a low bias. It's quite controlled, I would say. The main problem from this is you only rely on surface level. So you don't really look at the semantic, the meaning of what you are processing. You only look at how it looks. So you can sometimes remove a bit too much, I would say, or too little. You can miss some paraphrasing, for instance. Another way to do filtering, the second one, is to do some machine learning filtering. So it's quite different. You will take a set of example of good and bad documents, and you will train some form of a classifier on them. So it can be a fast text classifier, basically, or it can be a small language model, and you use the perplexity as the measure. You put a threshold. The nice thing about this is you have more like a quality filtering, like a content-based filtering. So it will kind of look at the semantic of what is in the data. So for instance, if you want to filter advertisement, you can do a filter for ads, for advertisement. The slightly less good thing is you have some bias in terms of the example that you give. You don't really know exactly what you will remove, right? It's ML based. You only know what you use to train the classifier, but you still have a little bit of a black box versus when you want to understand the decision of your classifier. I think on data filtering, one important thing is some domains should be manually inspected. So for instance, if you want to process math data, there is a very nice data set called Open Math. You want to be careful that you won't filter out, for instance, LaTeX or like, math equation. So for many domains, you will want to have a bit of custom rules. And probably you want to manually inspect the results. So usually what we do at our place, we extract, for instance, 10 documents per domain. We look at how they are processed. We manually inspect the result of each filter. And you should do that also for each language if you have several languages. Now, once you filtered, you want to deduplicate. The reasoning is that on the web, you have a lot of copy of page, and this will kind of artificially upsample some areas. So it can be good if it's a copy of maybe a Wikipedia or like some knowledge base. But if it's just a copy of a template, JavaScript template, or if it's a copy of advertisement page, it's quite bad because your model will want to generate this a lot, but this is not good quality content, right? You have several ways to deduplicate. It can be more fuzzy, where you use some Bloom filter or min hash. Min hash is what we use ourselves a lot. Or it can be exact deduplication with some technical exact substring with suffix array. There is a lot of trade-off in terms of speed of memory, because when you deduplicate at the billion token size, you can reach some pretty crazy memory requirements. So usually I would say min hash is a good trade-off. That's what we use. There is some counterintuition in terms of deduplication. And if you read our fine web blog post, you will see a lot of stories around that. Basically, at some point, you can stop deduplicating. You don't need to deduplicating to the max. I would say you want to remove the very large cluster where you have like 100,000 of identical documents. But if you have 10, 20 copy of a document, of a Wikipedia page, of a citation, this is just fine. You should not push too much. Now you finished preparing your data. So it's important to shuffle it, but this you know, right? That's the ML practice, but people still keep forgetting. We were working recently with Andrzej Karpati, who is quite knowledgeable in the field, and we had a big problem. And the problem was just that he forgot to shuffle the data. So it happens to the best of us, I would say. So don't forget about shuffling. Then you need to tokenize your data. Tokenization can be a bit of a rabbit hole because you have so many options. But here are some generic good practice. To train, you will train your tokenizer. To do that, you should sample quite widely in your data set so that your tokenizer is not overfitted to a small subset. I think a good example here was a tokenizer from GPT-2, which was very overfitted on Reddit data. It has a lot of, like for instance, Redditor account name in the tokens. So you don't want to overfit too much, so sample widely. Be careful of mathematics. You will probably want to split the digits or to put them manually in your tokenizer to be sure you cover all the digits fairly. For code model, you want to be careful about indentation and spaces. And yeah, obviously, depending on you have a lot of other specificities that you want to be quite careful. Also for language who have a lot of tokenizer are built with the notion of words, right? But in many languages you actually don't have a notion of words. So you need to be quite careful about this thing to make sure your tokenization is quite fair. I think there is a nice video. I was talking about Andrzej Karpati. He has a nice recent video on tokenizer and all the pithole that you have there. So you can watch this. Tokenization can take a surprisingly long amount of time to process for trillions of tokens. So you have two basically ways. You can tokenize dynamically during the training. It's quite nice because you can change your tokenizer. And the main issue is when you stop your training and you restart, it's a bit hard to know exactly where you were stopping because it's kind of all dynamically done. What we do here is you pre-tokenize and then you can just split your data so it's quite parallel to process. Now, the elephant in the room is how do you evaluate the quality of your data? It's quite hard because at this size of data sets, manual inspection only give you a very tiny glimpse in your data. What people are doing right now recently, and there's several paper published this year, in particular, so the fine web paper, is they use a set of high signal benchmark. So here I listed a set of high signal benchmark for English, but if you have also multilingual, you will want to extend it a bit. And I indicate a bit how to select high signal. You want something that's monotonically increased during the training, You want a low variance, so you can rely on your signal. And there is some tricky details. You have several ways to formulate your prompts and to evaluate your performance, and it can depend on whether your model is small or larger. There is a nice paper called Olmes recently, Allen AI, that can go in depth over this. I still think manual data inspection is very important. Taking a manual look at your data can very often be surprising. So don't forget to do that, even if it sounds a bit crazy when you just manually look a couple of pages in a trillion document. You can smartly do that, I would say. A very funny way to inspect your data is actually just to train a tokenizer on it and to take a look at the most frequent or like the less frequent on the longest token, and to see if you have a very weird token. It means you may have some very weird stuff still in your data. So we have a library called a data processing library that you can take a look. And we also have an evaluation library called LightEval that you can also check. Basically, they are both made for this type of tasks. Now let's dive a bit in modeling, and I will try to cover briefly the recent technique that people use in models. So when you train a large language model, there is a set of important parameters to be aware of, and most of them are around how to train efficiently. So you want to parallelize the processing. You want to use your GPU or your accelerator efficiently so that they are not waiting for the CPU to call them. You want to have some efficient way to do the attention. And then you want some stable training recipes. And you have a bit of more recent exploration. I think one which is very interesting is the mixture of experts. And another interesting one is Mamba, which is a non-transformer based architecture. So that's quite interesting to see a new architecture in the field. So I cover a bit the various ways to do parallelism. You have basically four ways to do parallelism, called 4D parallelism somehow. The one that many people use is data parallelism. It's very easy to use. Slightly more complex is tensor parallelism. Pipeline parallelism is even more complex, and sequence parallelism is a more recent one, very interesting as well. So data parallelism, usually it's very easy to implement. You just need to be careful with data loading. How it works, you will just copy your model on various GPU, and you will feed all the GPU different part of your data, and then you will just sum the gradients. The main challenge when you scale data parallelism is at some point, the gradient average over all the GPU start to be your bottleneck. You have a big step here where you need to communicate the gradient across all GPU, and these gradients are quite massive. It can be really the bottleneck at some point when you scale. And another limitation is because you copy your model, you have a batch size which is naturally increasing, which is usually good up to a certain limit, and at some point your batch size is actually just too big, and so you're training less efficiently. You're using less well each data sample if you want. So there is basically a limit to scaling data parallelism, and that's why we need some other techniques. And the first one you can tackle is tensor parallelism. Here it's slightly more annoying to implement because you need to rewrite the model code. So the way tensor parallelism works is you will divide your matrices either in the vertical like column direction or in the horizontal row direction, and you will put each part of the matrices on different GPU. Each one will compute independently, and then you sum the output. So you need to rewrite your modeling code because you will need to handle this splitting of each multiplication. It's also a bit more complex because you have potentially a synchronization point at each matrix multiplication in your model. So that can be quite a lot of synchronization point between your GPU. So usually what you will do is you will keep tensor parallelism where you have a very fast network between your GPU. So the way a data center is structured is usually GPU are clustered in nodes. So typically these are nodes of 4 or 8 GPU, where you have a very fast interconnect. Usually they can directly talk to each other without the CPU, without anything. And then these nodes, they are connected with smaller, like slower interconnect. So we'll do the TP internally on the node, but not through the slower interconnects. And then you have pipeline parallelism, which is the last part. And here the idea is you will put some layers on some GPU and other layers on other GPU. So you have less communication needed because you only communicate when you switch from one group of layers to the next one. But the danger is while you are processing the second part of your model, maybe the GPU for the first part are just waiting and they are not being used. And that's very inefficient. So the challenge is here to keep all the GPU busy at the same time. So you will want to divide the way you do that is you will divide your batch in smaller batch, and you will try to organize all this computation smartly. So as you can see here, it can be quite complex. Here you see the forward pass in blue, and you see it go from one to the other to the next, GPU. And we divided the big batch in smaller batch. So we have 4 smaller batch that you see numbered. And then you have the backward pass, and they can start a bit while some forward pass are still going. And so basically all the gray part here on this graph is what we call the bubble. So it's either GPU, it's GPU who are just, taking a coffee, they are waiting for the next batch. And that's something we don't want. So that's the tricky thing is if you use pipeline parallelism. And the last one is sequence parallelism, which is a bit complementary to tensor parallelism, because sometimes you don't have matrix multiplication that you can split. So I told you in tensor parallelism, you split your matrix in 2 and then you run them on 2 GPU. But for some operation like layer norm, for instance, or dropout, they are independent for each token. So you cannot really split the matrices. It's not a matrix multiplication. So here you can still do some parallelism on part of the model by splitting the sequence order. So, model take a big sequence as input, you split the sequence in 2, and for this part of the model, you will run one sequence in one GPU, one sequence in the other GPU. It's quite interesting. Be careful when you search for sequence parallelism, because there is 2 very different techniques who are both called sequence parallelism, which is a bit annoying in my opinion. So one is the one I told you where we split on the sequence, and another one is called ring attention. And this one is a way to extend your sequence and to do a self-attention over very, very long sequence. It's also interesting. We publish a blog post on this in a couple of weeks, but it's very different from the other one. If you want some reference for the parallelism, all the way to parallelism, it's actually quite hard to find a single place with all the information, but I really like this first paper called Breadth-First Pipeline, which cover all of these. And the 2 other ones are the sequence parallelism paper. Another big challenge when you train on many GPU is how to synchronize, and in particular this communication overlap. So I already covered that a little bit, but here you have a graph which maybe illustrates a bit more. As I said in the beginning, when you do data parallelism, for instance, you have a big step of communication at the end, and you see it on the top here. You see this very big all reduce, and it can be as big as your computation. Like you can spend as much time just exchanging information as you spend computation. And so there is a couple of smart way to solve this issue, or at least to not just wait for communication with your GPU idle. And usually the general way is to overlap communication and computation. So you can do that on GPU. You have many what are called SM on a GPU, and you can use some of them to communicate some of the data while you are computing. So a lot of the work to be efficiently training is around trying to smartly overlap the communication with the computation so that you are always computing, A good example is in PyTorch directly. You have a data parallel all reduce, which already implement overlapping computation and communication. But that's one of the main challenge, I would say, in scaling. Flash attention is a bit complex, so I won't cover too much, but the idea is very smart, I would say, is when you need to compute very, very large matrix multiplication, like the attention matrix, which is typically a square of the size of the sequence that you have. You can also actually divide this in much smaller computation and use kind of a running average to keep the statistic that you need. And so that's basically why everyone is using flash attention. I would say there is no interest anymore in making more efficient attention mechanism. Well, if you were following the field maybe 2 years ago, many people were working on a very efficient attention mechanism, trying to fight the fact that it was in the square of the sequence length. But because now we have this basically way of just not materializing the attention matrix anymore, I would say this field of research has been roughly stopped. Flash attention too is just an optimization, but that's quite technical, so I won't dive too much in this one. And then the last part you need to know is how to train with stable recipes. And I would say cover a couple of things. The nice reference that you know maybe quite well here, because it's come from a team of here, which is the mini CPM blog post. There is a Chinese version, actually, an original Chinese version, which is very good as well. And so basically, when you want to train with kind of a stable training and avoid the divergence or the spike that you can have, I would say there's a couple of things you need to be careful, which are around how to initialize your model. Something people forget quite a lot in terms of hyperparameter search. How to tune your learning rate. And here it's quite interesting because for some time people were pushing for the cosine learning rate, but actually a lot of recent research show that you can just train with a constant learning rate and you just do a decay phase, and that's very nicely illustrated in the mini CPM blog post, and also a paper we did more recently at Hugging Face, kind of investigating this as well, which is you can just train with a constant learning rate and then you decay at the end and you get as good performance as a very complex cosine schedule. Now, maybe more recent development. There is two that you need to know if you want to know well about LLM, which is the mixture of experts. So the mixture of experts is the idea that you can route your token in one or another MLP in your model instead of all having them in the same MLP. And the nice thing is these various MLP, this multi-layer perceptron, they will be able to specialize a bit on some or other aspects of your data. And for a long time, this was actually not used. The main reason was that we have very inefficient way to compute that. This way, we're actually losing some token. So we had for each expert, we had a budget of token. We said like this expert can take 2 tokens as input, and that's the memory that we assign to it. And then if we were routing 3 or 4 tokens to this expert, we would just drop the additional token. And that was too bad because then this drop token could have been important. And so actually what changed the needle was code called MegaBlock, which is using a very simple sparsity, dense sparse matrices, which are mostly dense and a little bit sparse, so that they are very efficiently running on the GPU. And this changed a little so that now we have actually many mixture of expert code running. And so it's a very interesting thing. It's at least 2 things that have not been explored, by the way, which is having expert of various size. And this would be very interesting to explore. If you want an idea for a research project, I would do this one. And another interesting thing is for the first time since quite a long time, we have some interesting alternative to transformers. And these are all around, the most interesting are around the space state model, which are model with a memory. So basically looking a little bit like LSTM, but quite simpler, I would say, in some way. And one which is interesting is Mamba. So it's quite technical to explain. I would say it's much more complex to describe than the transformers, unfortunately. But the nice advantage is it's running faster, I would say, in inference. Because at least you reduce the attention computation. So that's quite interesting. Well, the first experiment we did around the past month, we've been training Mamba, Training Phase quite a lot. It's not yet exactly comparable to transformers, and probably the ultimate architecture is a little bit between the transformer and the Mamba, with some transformer layer and some Mamba layer. So I would say the jury is still a bit open if Mamba will be an architecture that will find wide usage or not. We have a nice library called Nanotron, where we implement all of this, including MOE, Mamba, etc. So you can take a look at this one. Now, a last quick word, so you can find a lot of information on this. So I will go a bit faster. But once you have pre-trained your language model, usually you want to align it. And here is quite interesting because we're using reinforcement learning, right? It's quite interesting because for a long time, reinforcement learning was exciting topic, but also it didn't really work. But for a language model, it does really work. So that's maybe the most impressive example where reinforcement learning is used in the wild. And the way it works is that we were able to train some nice reward model from human feedback instead of having to manually define the reward like I show on the left, which is the traditional reinforcement learning where you do a very complex reward function, manually doing that, and then it's overfitting a lot on your environment. And here we just train a reward predictor from human feedback. The first example were very impressive in terms of performance, but also very complex because you needed to fit 4 models in GPU memory. So more recently, there were a lot of development, including something called DPO, which is much simpler because you only need 2 models in memory. And it's also training with, so this equation look complex, but actually quite simple. It's a training object that is quite close to the supervised pre-training objective. So it's really, much more common NLP technique than reinforcement learning. Though there is still some challenge, at least not really some challenge, but some people pushing for reinforcement learning technique, like the reinforce algorithm. So the jury is still quite open whether DPO and these more simple techniques will win. And then when you deploy in production, here there is a lot of information online, so I go quite faster. Basically, you want to quantize your model. You have many ways to do that. Here is a comparison of all 3 techniques. They all work quite well, to be honest. It's quite surprisingly quite easy and efficient to quantize model. You have some smart way to do speculative decoding where you use 2 models in parallel, a small one that go very fast and a large one that check the result of the small one. And you have some smart way to compile a model to go even faster in inference. And the last step, if you've trained a nice model, if you align it well, is you can share it or you can evaluate it. And so here you can check what we have at Hugging Face. We have a nice open LLM leaderboard where we compare all the models on a set of benchmark. You have LMC's Chatbot Arena, which is also famous. And you can also push a demo of your model on Hugging Face. And with this, I thank you